So in today's video we're going to look at the chain rule for derivatives. The chain rule is quite possibly the most powerful and most significant rule we have in differential calculus. So let me first go ahead and write it out at the top. The chain rule, formally defined that the derivative with respect to x of the composite function f of g of x is equal to f prime of g of x times g prime of x. Now, a basic review of our composition rules to kind of get our minds around what this is saying. If you have a function, say f of x equals x to the third, and you have a function g of x equals x plus 7, then f of g of x is where you just plug in this g of x for every x value on f of x. So it would be x plus 7 to the third. And that's just our basic rules of composition from algebra. Well, the chain rule allows us to take the derivative of a function like this. So the chain rule tells us that the derivative would be f prime of g of x times g prime of x. So say in this example, f prime of x would be 3x squared, just taking the derivative of this function. So this would be f prime of x. Well, g prime of x, the derivative of this function over here, is simply 1. So the derivative of f of g of x is going to be f prime of g of x, which is x plus 7, times g prime of x. So it's simply 3 times x plus 7 squared. And this is a pretty simple, straightforward example, but as we'll see moving forward, we can use the chain rule in a ton of different situations. So let me give a little more elaborate problem, and we'll look at what we can do with this. So say we have a function, or an equation simply, that y is equal to x to the third plus 7x squared minus 2 raised to the 10th power. Now if you wanted to, you could multiply that out and get it in a basic form where you could use your power rule, but if you did that, you're going to have probably 40 or 50 terms, and it is going to be a very long, ugly mess. Not to mention it would take all day to multiply it out. But using the chain rule, we can say that our f of x is equal to x to the 10th, and g of x is equal to x to the third plus 7x squared minus 2. Because if this is the case, then f of g of x is going to be x cubed plus 7x squared minus 2 all to the 10, because we're just plugging in our g of x for our x value on f of x. And this is just a basic review of the composition of functions. Well, with that in mind, we know our derivative is going to be f prime of g of x times g prime of x. So what is that going to look like? We know that f prime of x is going to be 10x to the 9th, just using the power rule with this. So f prime of g of x is going to be 10 times g of x to the 9th. So x to the third plus 7x squared minus 2 to the 9th. And then that's multiplied by g prime of x. So we'll just use our power rule on this g of x and get 3x squared plus 14x. And this is our derivative using the chain rule. So as you may notice in this, it's a lot like the power rule, where we're just dropping the power from here out in front, dropping that power 1, but the difference is since there's a function inside, you just take the derivative of that and multiply by it. So that's a basic chain rule example when you're working with a polynomial that's just raised to some power. So let's look at one more example in this video. Say we have y is equal to the sine of 2x. Now to take this derivative, this is a composite function when you think about it, because f of x is equal to the sine of x, and g of x is equal to 2x, which makes f of g of x the sine of 2x. So we can use the chain rule here to take our derivative. F prime of x is cosine of x, but we want f prime of g of x, so it's going to be cosine of g of x, 2x, multiplied by g prime of x. Derivative of that is simply 2. So we get dy dx is equal to 2 times cosine of 2x. And this is just another example of how we can use the chain rule that opens up a lot of potential derivatives that we couldn't take with any of our other rules. And I think this is what sets the chain rule apart, as being so powerful, and how we use it in a lot of different ways as we move forward throughout calculus.